So for our warm-up, just for the video purposes, when we were finding these limits for this first one, you just plug a -1 into this function and you get -8. Here you plug a 2 into the function y equals 5. It doesn't matter what you plug into y equals 5, the y value is going to be 5. And for the last one, you plug a pi into this function, you get pi times -1, which is -pi. All right, so today's lesson is 2.3. I can calculate limits algebraically. This is a big lesson. There's going to be a lot of stuff, not a lot of fun, mostly just grunt work, because it's a big algebra day. So we won't have any board work or cutesy activities today. We do get one little brain break, but it's mostly just going to be a working day. So people watching the video, get ready. You have a lot of work to do. Here we go. Okay, this first, don't freak out. Wait, Ryan's freaking out. Okay, don't freak out. You don't write this down. All right? Okay, so this first slide is just to show you the properties of limits. And I will tell you, this will be in the Smartboard notes. It'll be on the screencast. You don't need to write all of these down. You won't be tested on memorizing these or anything. All you need to know is understand them intuitively. I'm going to walk you through them for just a minute, and then we're going to move on. So the first two properties say that the limit of the sum of two functions is equal to the sum of the limits, and the limit of the difference of two functions is equal to the difference of the limits. So, for example, on our first warm-up problem, if I rewrote this as the limit as x approaches -1 of 3x to the 5th minus the limit as x approaches -1 of 2x squared plus the limit as x approaches -1 of 7x plus the limit as x approaches -1 of 4. This, if I took each of these limits separately and added them together, I would get the same thing as if I just plugged it in all at once, right? So those first two properties are just saying, I shortcut them and say, hey, the limit of the sum is the sum of the limits. So if you have it all in one, or if you separate them out, it's the same. You're going to get the same thing either way. All right. Okay. Next property, this third one here, this C right here, this C, that's a constant multiplier. I call it a scalar. So we do a lot of vectors when you get into Calc 3, and so I like to use those terms throughout this year to help get you ready to go into Calc 3. So whenever we have a constant multiplier times our function, call it a scalar. It's just a number times your function, right? So what does it mean when we have a limit of a scalar times a function? You can move the scalar in front. All that's saying is if I have the limit as x approaches 2 of 3x squared, that's the same thing as 3 times the limit as x approaches 2 of x squared. You can take this constant multiplier and put it in front, and you'll get an equivalent answer. That really doesn't, just so you know, for all these properties, most of the time when you're plugging numbers in, you're not at all thinking about these properties, but it will come up from time to time when we get into more complicated limits. This is just to kind of get you familiar with them. All right, so same thing here. If you have a limit of a product, it's the product. You can do each limit separately and multiply the answers together, right? So same kind of thing, like the x cosine x, right? If I did the limit as x approaches pi of x, times the limit as x approaches pi of cosine x, and multiplied those answers together, I get the same thing as the limit as x approaches pi of x cosine x. All right, same thing for division. The only thing about division you have to be careful with is if you divide by 0, right? So division obviously doesn't work if you're dividing by 0. You get a limit that doesn't exist, or it might be indeterminate. We'll get into that later on. But as long as this limit doesn't approach 0, divide away, life is good. All right. This guy, if your function's raised to a power, you can take the whole limit and raise to a power. So for example, for number 6, if I had the limit as x approaches 3 of x squared, that would be the same as the limit as x approaches 3 of x squared. right? So you can take the whole limit first, then raise it to the power either way, right? Whatever works. All right, so that's fine. Just so you know, jumping to 8. 8 says the nth root, same kind of thing. I almost think of these as really the same property because you can write an nth root as an exponent anyway, so it's really just the same thing. This little guy right here is that limit of 5 that we did in the warm-up, right? The limit of a constant is a constant. So because of the horizontal line thing, right? So limit of a constant is a constant. Those are your limit properties. You don't have to have them memorized. You just need to understand that those are true. These are true things about limits. Any questions on these things? There's nothing real surprising, right? It's pretty basic. All right. All right, moving on. So we have one fun little group problem, and I'm just going to have you guys work on it. So I'm going to give you about 2 minutes in your groups. I want you to do A, B, and C. This is partially to check the properties and partially to promote a little discussion where things might get a little, might be a little bit, I'm just not sure. And then you can talk with your group members. So I'm going to freeze, and I want you to work on this for a couple minutes, and I'm going to kind of move around the room and see what you guys talk about. All right, so just try on 3 on paper. You can figure out these 3 limits. All right, are they working?
It's from both sides. But you don't need an actual point. You just
Well, what about the other line?
Oh, wait, negative.
The line not that.
No, that's G. That's G.
Oh, the limit, yeah. It's the first part A is the limit as x approaches -2. Yes.
So that's when they're
Or wouldn't it be 1 minus 1.5 times negative 1?
Oh wait, that's 1. Just kidding.
Oh, wait, never mind. That was
So I guess B is. Oh, actually, the limit for G doesn't make sense. That means it doesn't make sense.
the whole thing's fake. It's all a lie.
Oh,
Right, now you work on C.
wait, that one actually.
No, now you're holding.
No, this one's not.
Oh yeah, it does. Yeah. No, because well, because G of X. So that's like 2 is 0. Oh yeah. So yeah, it's over. Well, I guess B.
I thought it was.
Yeah, I know.
Oh, yeah. The F is.
So what B?
I said yeah. Because like it's on the thing. Like G doesn't get to. You can't multiply something. Yeah, I just said B.
Did you say that for?
Oh, I'm still working.
So
Yeah.
But we were thinking because like since G of X, when the G of X limits this,
Yeah. Okay. Yeah.
I know there's 2 of them, right?
and if we're safe, because of the G of X.
Yeah.
But A is there for it.
Yeah.
You see where it's
School starts like the first day of the start.
the first thing I'm sorry.
After that, I did. I usually don't.
Wait,
Yeah, I know, but like, Well,
is it though?
important?
Is it?
They say important.
It is.
Technically, right. I mean, it is important for the metabolism.
Yeah.
Well, I probably know what it is.
Like, how do you describe it?
Is it like eat like food that does like
Yeah.
Yeah, that's fast. It's for, wait,
No,
I only
it's not
eat
digesting. It's like
like
for burning.
Yeah.
But wait, I only breakfast. So it doesn't look like
No, because that's that naked. That's that one.
How about the math?
I need to like think about it.
Actually, I had one.
Isn't that right?
Because the limit comes from the limit.
Oh, the limit.
All right, we have some fun, so we're gonna walk through these.
Wait, is that a negative?
It's still -1 is -2.
Time. Awesome. So you just got so people who are watching, you just got an extra 6 minutes of staring at a screen that didn't change. Okay, so that's good, but they got to hear the general murmur of you guys working, which is nice. You guys probably the most are on that audio recording. All right, good. So for the first one, whoops, you could rewrite this as the limit as x approaches 2 of f plus 5 times the limit as x approaches -2 of g. So then we kind of break it apart, so limit by limit. So Tarun, the limit as x approaches -2 of f, f is your red function. What's the limit as x approaches -2? 1. It's 1. Good. Plus 5 times, Tarun, what's the limit as x approaches -2 on your g function? -1. So 1 plus -5, your limit is -4. Now, you do not have to write all that out. I'm just writing it out so you understand where the number comes from. But how are we doing? Did everyone agree on -4? Yes, got a lot of head nods. All right, good. All right, that one I think was okay, pretty straightforward. The next one was a little bit of extra fun. So moving to the middle group. Hi, Jennifer.
Hi.
How are you?
I'm good.
Good. So Jennifer, what's the limit as x approaches 1 on f of x? So here's 1, here's f. What's the limit?
2.
2. What's the limit as x approaches 1 on g of x?
It doesn't.
Why doesn't it exist?
Because coming from the left and the right, they.
Good. Not the same for both sides, right? Point to 2 different y values from the left and the right. Is that okay? Oh, okay. All right. So because the limit as x approaches 1 on g of x does not exist, you have a limit of 2 times dne. Jennifer, what's 2 times dne? It is dne. 2 times non-existent is non-existent. You can't take non-existent and double it and get a number, right? It's still going to be non-existent. Okay. All right. Good. Any questions on part B? All right. So Luke. Hi, Luke. All right, let's take a look at part C. So we have the limit. Let me erase this a bit. The limit as x approaches 2 of f divided by g. So the limit as x approaches 2 of f, give me like a rough idea. What do you think that is? It's around 1.5, right? All right, Luke, what's the limit as x approaches 2 on g of x? It's around 0. 1.5 divided by 0 is bad, right? Okay. In limit world, or just in the graph of this function, if f over g was like one function and we graphed it, what would we have on that graph at x equals 2? We have not 0 over 0. We have a vertical asymptote, right? Good, and way to help out your group member, right? That's what you're there for, help and support, right? Good, they're absolutely right. We have a vertical asymptote at x equals 2. Whenever we have a vertical asymptote, add a number, what do we have to do? We got to find the limit from the left, find the limit from the right, and see if they match. Because if they match, then you have to write the infinity or the negative infinity. You can't just write DNE, right? Okay, so let's check it from the left and the right, which I'm sure you all did, right?
Yeah.
Yes. Okay, totally. All right. So, whoops, I can't find the equals yet. So we're going to do the limit as x approaches 2 from the right of f over g. All right, I'm going to move this out of the way a little bit. I'll leave this and I'll rewrite this, but I'm just going to write it. All right, so Vishali. Hi, Vishali. All right. So as x approaches 2 from the right, remember that when we're doing vertical asymptotes, we're just checking the signs. Is f, as we approach 2 from the right, on f, are we positive or negative? Positive. On g, as we approach 2 from the right, are we positive or negative? Okay, you sound really certain. Okay, so let's make sure we know why, right? Okay, here's 2, right? There's 2. If we are any value to the right of 2, are we above or below the x-axis? Above, so we're positive, right? Good, see, you knew it. All right, so now we have a positive over positive. This limit is approaching what? Positive infinity. Very good. Does that make sense? All right. Let's try the negatives. All right. That's just kind of an extra string marker. Let's see. Who haven't I called yet in that group? Ryan. Hey, Ryan.
Hello.
How are you? Good. All right. So now we're going to approach 2 from the left. On F, we're on F now. As x approaches 2 from the left, are we positive or negative? Positive. What about on G as x approaches 2 from the left? Negative. What does that mean? How do you know you're negative?
Because any number to the left is below the
Yes, that was beautiful. Did you guys hear that? Any number to the left of 2 here on G is going to be below the x-axis, right? So we are positive over negative. This guy's going to negative infinity because the limit from the right goes to positive infinity and the limit from the left goes to negative infinity. Ryan, what's the limit as x approaches 2? DNE, which something tells me most of you got, but something tells me most of you probably didn't have your appropriate justification, right? Okay, so now we know. Whenever we say DNE for vertical asymptote, I'm going to check. Did you check from the left and the right? I want to see that. Okay, so vertical asymptote, remember you got to check left and right. I want to see those left and right-handed limits. Whenever you're talking about a vertical asymptote, I want to make sure you know why you got what you got. All right. That was just a fun one. That actually had nothing to do with today's lesson. So, all right.
Why are we doing this?
That's for fun. Okay. All right, so here we're in the first part of today's lesson, direct substitution. We're going to spend 10 seconds on this. If a function is continuous, and I know you guys don't know yet what continuous means. Most of you have heard the word, though, right? Did you all hear the word continuous in pre-calc? Yes, okay. So continuous, we're going to talk more in depth about what it means starting tomorrow. But for now, just, yeah. Whenever you have a continuous function, you can plug in the number and the answer that you get is your limit. For all intents and purposes, continuous for this class means there's no holes, there's no asymptotes. If it's a piecewise function, then you got to do a whole bunch of other stuff. So no piecewise. If there's a radical, make sure you don't have like a negative in the radical, right? But basically, no holes, no asymptotes are your two big things to check for, right? So you're not, essentially, are you dividing by 0 or not, right? If you're not, then it's pretty safe. You could just plug in the number. So moving to, do I want to go the left or the right? Which way do I want to go, left or right?
Right.
Right? Okay, I'm going to go to you guys first. We're going to go back to front. So, Emma.
Yeah.
Hi, Emma.
What's up?
Oh, not much. What's up with you?
Not much.
Really?
Yeah, just doing math class.
Spent Saturday in the rain?
Mhm.
Yeah, out on the marching band field. Yeah.
Yeah.
Okay. So, but you know what? Those are stories you can just look back on. Once it's over,
Exactly.
yeah, you know, kind of fun, right? Remember that day we had to do marching band in the rain? All right. So, Emma, when you plug in a 2, what's 2 squared?
4,
4. What's 2 times 3?
6,
What's 4 plus 6? See, you rock, right? Monday morning, perfect start. 100%. Well done. All right, any questions on plugging it in? Plugging, there's no really, that's a really poor math term. It's direct substitution. Any questions on direct substitution? All right. I always try to use good mathematical terminology, except this is honestly a failing of mine. I do say plug it in all the time, and I really shouldn't. I should say substitute. Substitute 2 for your independent variable. All right, squeeze theorem. You don't even have to write it down. All right, if you want to, you can. I will never test you on it. The College Board is probably not going to. I don't think, as a matter of fact, I think I could say definitively they're not going to test you on it. It's just that it comes up from time to time, and so I just want you to be familiar with it. It's not one of those heavy-duty theorems. There are a couple theorems you're going to learn this year where you have to know them inside out and upside down. You have to be able to state the hypotheses and state the conclusion and justify and recognize when to apply it and how to apply it and how to prove that it applies and all that kind of stuff. There are a couple theorems we'll have to do that. This is not one of them. This is it's just a random theorem that you need to kind of be familiar with. So here's the gist of the squeeze theorem. The squeeze theorem says that on some open interval, so it doesn't have to be the whole real number line. Like for this picture right here, it could just be like from there to there. Some open interval containing some point. So you got some open interval. If on this open interval, you happen to have one function that's always on top and one function that's always on the bottom, and those two functions happen to have the same limits at some point in that interval, all right? So you got a function that's always above, a function that's always below, and they meet up at some point, right? They don't have to have y values, they can both have holes there, but they have the same limit at that spot. All right, if for some crazy reason you've got some third function coming along that is in between those two, then that third function has to have the same limit value at that point because it's squeezed in between the other two functions. So how do we use this and why do we use this? Well, the most common example for squeeze theorem is the proof of the limit value for sine x over x as x approaches 0. So if you plug in a 0, what's the sign of 0? 0. To be able to shout it out. What's the sign of 0? 0. 0. Good. And then you plug in a 0, you get 0, right? So if you plug in a 0, you get 0 over 0. But what do you do with that? Like there's a hole there, right? Because it's not 0 over 0, it's 0 over 0. We know there's a hole, but how do we find the y value? I mean, you can't cancel, you can't factor, there's nothing you can do. You're just kind of stuck, right? So there is something we could do that you'll learn later on called L'Hopital, which is great and easy and so much easier for doing this than squeeze theorem. But right now you don't know it, so you have to learn squeeze theorem. So lucky for us, sine x over x happens to be easily squeezed in between two other functions. So the two other functions that sine x over x is in between are the horizontal line y equals 1 and this lovely curve right here, which is y equals cosine x. So this is y equals 1. This is y equals cosine x. As x approaches 0, what's the limit of 1? 1. Just whole class just answered. As x approaches 0, what's the limit of cosine x? 1. So they have the same limit, right? So because the limit as x approaches 0 of 1 is 1, and the limit as x approaches 0 of cosine x is 1, since sine x over x happens to be squeezed in between these two functions, we know then by the squeeze theorem that this limit is 1. So the limit as x approaches 0 of sine x over x is 1. Why? Well, we can prove it by the squeeze theorem. Okay. So anyway, that's just a quick snapshot because you might see those words from time to time. I think there might be a little mention of it in your homework tonight. Just know squeeze theorem just means that if you got a function above and a function below and they meet at a spot, then anything in between will also be forced to have that same limit at that spot. All right. Moving on. Now we're actually into the stuff. So before we get into examples, we have to learn one little like vocab term, which are these words called indeterminate form. Indeterminate form is what we call a limit when if you initially plug in and get 0 over 0. There's actually other cases that we will get into, you will get into in BC. So anyway, I won't because I'm not teaching BC. But you guys will. So later on, you'll get into really fun ones like infinity minus infinity and 0 to the 0 power. Hey, is 0 to the 0 power 0? Or is 0 to the 0 power 1? Ooh, dun dun dun, right? Okay, so that's what you're going to discover. So anyway, so those kinds of limits, but today and for all of chapter 2, just know that whenever you see 0 over 0, that's called an indeterminate form, and all it means is that the limit in that form, it can't be determined. You have to modify the form somehow so you can figure it out. That's all it means. So indeterminate means undetermined, right? The limit is not determined yet, but that doesn't mean it can't be. It just means in that particular form, it's not determined. Whenever you have 0 over 0, that means there's a hole there, which means the limit exists. Keep going. 0 over 0 means keep going. So in limit world, when you see 0 over 0, you keep going. There is a limit. It's there. That's your job, is to find it. Okay? I put 98% of the time because you can, using some really evil manipulation on a piecewise function, force a limit to be 0 over 0 that doesn't exist. But we wouldn't do that, like, and neither would the College Board. But I will tell you, there is a way to have a limit that is 0 over 0 that doesn't exist, but it's really rare. You have to really think and like intentionally manipulate to make it do that. But anyway, so but for you guys, 0 over 0 means keep going. The limit exists. All right, what's our favorite F word? Factor. Our favorite F word is factor. So first thing is when you see a polynomial over a polynomial, well, first thing you always do is plug in, right? So if we plug in the 1 on top, what do you think we get? 0. What about on the bottom? You get 0. 0 over 0 in limit world means keep going. The limit exists. So whenever you have polynomial over polynomial, that means factor, right? So go ahead and everyone take a minute in your groups and factor the top and factor the bottom. Ishan is like, this is his favorite thing in the world. He's been talking about it all day, how he loves factoring. Yeah. I'm going to pause it. When I factor, I personally factor by guess and check. There's a lot of different ways to factor. I was taught how to factor in the 80s. Back then, we were taught guess and check, and that was it. Now there's a lot of other ways, but, you know, whatever. So, oops. Wait, go back up. All right. So I'm just going to show you when I am factoring. I'm going to rewrite my limit here. So x squared, I think x and x. 5 can only be 1 and 5, or 5 and 1, and it makes no difference because those are both just x, right? So then you look at your signs. This is positive, means you either need plus plus or minus minus. To make that a negative, you got minus minus. And then I mentally always multiply it back out. I always do this. So I think x times x is x squared. Negative 1 times negative 5 is 5. And negative 1x minus 5x is negative 6x. I always go through that process when I'm factoring to make sure that I did it right, because it's really easy to mess up factoring. Especially this bottom one, there's a very deceptive incorrect answer that's really tempting. So when you factor the bottom, you have this 2x squared. So you have a 2x and an x. So if you do the 3, you either have a 1 and 3 or a 3 and 1. So it's really tempting to go 1 and 3 because you think 6x and an x. Oh, 6x minus x, that's my 5x, right? So I do a negative 6 and a positive 1. Negative 6x plus 1x, got my negative 5x, life is good, right? What is wrong with this? It's not a positive 3, right? Plus 1 times minus 3 is negative 3, so it doesn't work. So instead, I do this. I do, oh my gosh, x. Erased everything. So 1, 3. Okay. So now they got to be both minus minus to make this middle one a minus. Negative 3x minus 2x, negative 5x, life is good, right? So make sure you're checking your answers. However you arrive at the factors doesn't matter to me, right? It's just getting there. As long as you can get there somehow, then you're fine, right? So, Ishan, did you get there?
Yeah.
All right. Okay. So, Ishan, once you get there, is there anything that you can do with those factors?
You can mentally cross out.
Or could you actually physically cross them out?
Why is that like you couldn't do that?
Ah, you can't do that in function world, but we're in limit world, and in limit world, you can cancel
Can we
to
physically?
your heart's content, right?
Can we like actually cross them out on the page?
So personally, if I was doing this,
Yes.
you can't cross out in a function because you're changing the domain, but the value of the limit is the same, whether they're there or not. So because of that, absolutely you can cross out in limit world. So when you're in limit world, you can cross out common factors, and you end up with this guy, which when you plug in, you end up with a positive 4. How many of you guys got a limit of 4? Fantastic. Okay, we have some things to talk about. There is a note here. Always rewrite the limit statement for every single step until you plug your number in. Now this is really important. We will take off, and the College Board will take off, if you don't rewrite your limit statement every time. They consider it bad notation. When I used to teach at my old school back in Georgia, I would take off a point for every single missing limit statement. So even if the problem was like really big and had like 7 or 8 steps, then you could lose easily 7 or 8 points on a problem. Even if the problem is only worth 3, I'd still take off a -7 for 7 missing limit statements, right? And so I always love that, because I'd always have students once in a while who get a negative score on a quiz, right? And so I used to like say, well, is it fair? Well, you know, there's an argument you could make for entering a negative score in for a quiz grade. But I was always nice. I always rounded up to 0. So anyway, so in this class, I will tell you on your test, if you have missing limit statements, we just take off a point per problem, which is still a big deal because I think the whole test is only 50 points, so a point is a major amount, right? So don't lose a point for missing limit statements for bad notation, right? Okay, if you're going to lose a point, I always say, like, lose it big. Like, you really don't know what you're doing. Don't lose a point for notation. All right, so here's the thing. So every single time you're doing a limit, if you don't have, say this was gone and say this was gone, you've just lied to me 3 times, right? Because you just said that this limit of this function, right, and a limit is a numeric y value. You said that this numeric y value is equal to this rational function, And then you said this rational function is equal to this rational function. Also a lie, right? Different domains. And then you said this rational function is equal to the number 4, which just is nonsense, right? So anyway, you can't lie. You got to have your limit statements every single time, or they are. I promise you, College Board's going to take off if you don't. So be very careful about your limit notation. The other thing I need to tell you is your algebra isn't graded. Like I'm going to look for setup. I might look to see that you factored, like look for your method. But from here, if you are able to jump from here to here, right, that's totally fine, okay? So, like, I don't need to see algebraic steps at all. What I'm really looking for is setup, method, answer. Yes?
Could you skip the, like, instead of the middle, you skip, like, that second step instead of the third step?
Well, I want to see factors, though. If you solve by factoring, I'd like to see the factors. So I think I'm going to say, no, I don't want you to skip this first step because if you're solving by factoring, I need to see the factors so I know that you did it by factoring. Good. Other questions? Let's move on. Method 2 is called, rationalizing. So for this beautiful problem, we plug in a 4 and we get 6 minus root 36, right? What's root 36? 6. So you get 6 minus 6, which is 0, over 4 minus 4, which is 0. This is 0 over 0. What's on the graph when it's 0 over 0? A hole. So does the limit exist or not exist? Limit exists. 0 over 0 means keep going. Do you want to try to factor this? No. This would be kind of a weird one for factoring, right? So instead, we're going to rationalize. You guys rationalized in the past, but you rationalized in order to get roots out of the denominator. We're going to rationalize to put a root into the denominator because we don't care where the roots are, right? In our class, 3 over root 2 is a beautiful answer. So it doesn't matter where the root falls. We just need to be able to solve the problem, right? So we're going to rationalize by multiplying top and bottom by this beautiful thing. It has a name, and let's see here. I called on Emma Zuhair, right? Yeah, okay. You looked at me like I was wrong. Are you Zuhair, right? Yes. Hi, Zuhair. How are you? I'm doing all right. Okay. We have to multiply top and bottom by something. Do you know what that thing is called? You know what to do, you just don't know what it's called? Okay, so first let's make sure we know our terminology. It starts with a C.
Conjugate.
It's the conjugate. Does that ring a bell? Okay, good. We're going to multiply top and bottom by the conjugate. Now, Zuhair, what is the conjugate of the numerator? Good. So you changed this sign, but you didn't change this sign? Is that correct? Are you sure? Positive? Okay, yeah, you're right. So you have, when you multiply by the conjugate, you change the sign that separates the terms. In this problem, if you look at the top, there's 2 terms. There's the 6 and there's the root x plus 32. The root x plus 32 is like one thing that's this beautiful united thing. You can't change it. So the sign that separates the 2 terms is this minus right here. This becomes a plus. Now, when you multiply the top by something, you also have to multiply the bottom, right? So we've got to multiply the bottom. Don't jump ahead because you're going to do something and I'm going to tell you not to do it. But before we do this, I'm going to just give it a tiny bit of background. Why do we multiply by a conjugate? It's because of x squared minus 4, right? So x squared minus 4 factors into x plus 2, x minus 2. X plus 2, x minus 2 are conjugates, right? Same terms, just different signs separating the 2 terms, right? So when I multiply 2 conjugates together, first times first gives me the first, last times last gives me the last, but what happens to the outer and the inner terms? They always cancel because they're the same, just with opposite signs, right? That's the whole point of conjugates, is that when you multiply them together, the outer and inner terms wash out and you don't get a middle term anymore, right? So what it's going to do with these guys is it's going to get rid of our root. All right, so here's what we do. By the way, if you have a problem that you know is going to have a lot of steps, no one's going to, I won't take off, it's fine, but I would suggest working vertically, because if you work vertically, then your limit statement will always just line up and you'll see real easy, like, oops, I didn't write my limit statements, right? So make sure the first thing, most important thing you write is to rewrite your limit statement. All right, Faith. Hi, Faith. Help me with the top here. So 6 times 6, 36. What's our next sign going to be? Minus. What's root x plus 32 times root x plus 32? X plus 32. And we're going to put that x plus 32 inside of what? Parentheses, because we need to make sure we distribute the negative, right? All right, I'm going to write a little rule down here at the bottom. Never distribute the denominator. Ever. You never distribute, see, this is why we don't work ahead. Okay, you never distribute the denominator because the denominator is already factored, and if you distribute it, you're not going to be able to see your factors that cancel. So you keep the denominator factored. So the denominator stays x minus 4 times 6 plus root x plus 32. Never distribute the denominator. Okay. All right. Mihika, what is the most important thing that I write next? It's the limit statement, right? Ah, good. All right. Okay. So, Mihika, if I combine terms on top, what do I end up with?
X plus negative x plus 4.
Negative x plus 4. Do you mind if I write that as 4 minus x? Is that the same? That's okay, good. All right. So I have that over that. Okay. Jennifer. Hi, how are you? I'm doing good. How are you? I'm doing great. Jennifer, do we have anything that cancels?
Yeah.
What cancels?
You can cancel x minus 4 and negative x, or negative x.
Ah, okay. So what Jennifer just said is this x minus 4 and the 4 minus x look really close, right? They're not exactly the same, but they're close. When you cancel them, you're not left with a 1, you're left with a negative 1, because the 4 minus x is actually equal to negative x minus 4, right? So when you can't, is that okay? Good? Okay. So when you cancel this with x minus 4, on top, you're actually left with a negative. So I'm going to rewrite Keegan,
Yes.
are you ready?
Yeah, totally ready.
Totally ready. Your question is, for my next step, do I rewrite my limit statement?
No, because you're going to plug in 4.
Yes, nailed it. Awesome. Okay, once you plug in a number, you don't rewrite because this limit is the number, right? So you just write the number. So everyone take a second, plug in the 4, see what you get. Are there any questions? Are we good?
Yeah.
Yes? Did everyone get negative 1/12? All right. That's rationalizing. We got to move on. I'm sorry. I know it's a lot today, but here we oh, brain break. All right. I'm going to pause. Those of you watching the video, you can just read this for yourselves. Where's my page thing? There we go. All right. Second favorite F word, fractions. All right. I want you to write the problem and don't work ahead. Just write it and then chill for a minute. You like complex fractions? Oh, good. I like complex fractions too. I should preface that. I like cleaning up complex fractions.
Same.
Yes.
Because it's satisfying.
You like that too?
I love that.
Okay. Oh, good.
I used to get it algebra.
There is something very satisfying. I also like canceling. Like there's something very satisfying about canceling. Okay. All right.
I hate like adding.
Okay, everyone have it written. Now, back in Algebra 2 or pre-calc, whenever you learned how to simplify a complex fraction, there is a very common method. And I actually watched this method get taught after school on Friday. There was a student staying after in a classroom, and the teacher was teaching this method. It's great. It's foolproof. It works fine. I don't want you to do it. And I'm not one to discourage methods. Like I'm very open. I'm not like anti-method, but I will tell you for sake of time and simplicity, I want you to learn my way. And I don't usually push my way. I'm going to push my way on this one. So here's the thing. So the method that you might be familiar with is you ignore this and you ignore this and you just look at the top. And you just treat it as though you're going to, combine those two fractions together, right? And then once you get those combined, then you kind of start saying, oh, but now we got this x under here, so then you flip and multiply and you got it, right? Okay. I don't want you to do that. We're going to cut a step out. So here's what we're going to do instead. All right, moving to the other side of the room. Alec, how are you? Good. Good. Alec, can you tell me the LCD of these fractions? The least common denominator. If your group wants to give you a nudge, they can give you a help. If you were to add those fractions together, just look at the top. If you were to add them together, what would end up being on the bottom? All right, I'm going to give you a nudge, okay? What do we do if I have to add like 1/3 plus 1/2? They have nothing in common. What do I do to get the LCD? You multiply them together, right? Same thing when there's x's in it. Beautiful. All right. So instead of writing 10x plus 4, though, we're going to think of it as 2 times 5x plus 2, but that's exactly right. Does everyone understand how Alec got that? Good. So here's what I want you to do. I do not want you to combine them. I want you to multiply the whole top by 2 times 5x plus 2 and the whole bottom by 2 times 5x plus 2. Later on, you'll get to a point where you don't have to write this anymore. You could just do this mentally. You'll amaze your friends that you can simplify complex fractions in one step without having to write anything. All right. So, Gavin, what's the most important thing that I write next? Close.
Oh, wait, limit?
The limit statement. Well done. Okay. Answer's a good one, though. All right, limit statement, because I can't jump from this to the answer. I got to do a little more writing. All right, so here's the thing. If I multiply this term by this, so I have 1 over 5x plus 2 times 2 times 5x plus 2. Gavin, what can I do with the 5x plus 2's? They cancel. So what am I left with when I multiply this times this? If the If the 5x plus 2's cancel, I'm just left with 2, right? 2. All right, Gavin. Minus stays minus. If I multiply this times a half, the 2's cancel. And what am I left with? 5x plus 2, which I should, of course, write in parentheses. Good, Gavin. All right, fantastic. All right, well done. All right, I'm going to take you off the spot. So when we multiply the denominator, should I multiply it out?
No.
No, because we never distribute out a denominator. So x times 2 times 5x plus 2, I'm just going to write it as 2x times 5x plus 2. Ari, are you ready? Okay, this is the question of the day. Look at this, what I have right here. First of all, is this still a complex fraction?
Yeah. No.
No, because a complex fraction is a fraction inside of another fraction, right? We have no more fractions in fractions. Complex fraction is gone. All right. Can I cancel these 5x plus 2's?
If you also cancel the. Technically, yes, but no at the same time. Yes, right. 2 over 2x. Yeah, and 5 as a negative 2, and then you can cancel.
Okay, so what Ari is saying is if I split this into 2 separate fractions, then I could cancel the 5x plus 2's from one of the fractions.
Yeah.
Would that help me?
Yeah, but then I'm like,
That kind of defeats the point of what we're doing, right? Okay, but so you are right. Technically, there's a way to make it happen, right? I could cancel from every term, and then I'd be right back up to here, right? Okay, I'm not going to do that, though. All right, so instead, just know, if you cancel something that's not in every term, that's bad algebra, and I'll write a big BA on your paper and take off points, all right? Okay, what does BA stand for? Bad algebra. All right, so instead, Ari, what would be a better thing to do with the terms on top?
You can do 2 minus 2.
Yeah, combine like terms, right?
Yeah.
2 minus 2 is gone, so what's left on top?
Negative 5x.
Beautiful. Should I multiply out the bottom?
No.
No. Fantastic. All right, Ari, last question. Is there anything now that cancels easily?
X.
X cancels! Woo-hoo! Beautiful. All right. Oh, okay. Well, you know what? I've questioned Ari enough. So let's just move on to Charles. Hi, Charles. How are you? Good? Okay. All right. I have canceled common factors, so I'm ready to plug in my numbers. Should I rewrite my limit statement? No, because I'm about to plug in my number. As soon as you plug your number in, right, you don't write your limit statement anymore. So if we plug in a 0 on top, what do we get? Negative 5. If we plug in a 0 on the bottom, we get 2 times the quantity 0 plus 2. What does that equal? Yeah, 4, right? So your answer to this limit is negative 5. Fractions, clean up the fraction, and then something will always end up canceling, right? All right. Moving on. This guy, let's see, how much time do we have? Not much. We have 2 minutes. All right, I'm going to work this so fast your head's going to spin. Are you ready?
yeah.
We have to do this too.
Yeah, when you see a limit where there's nothing to cancel, but you just, it says, square this, just square it. Do what it tells you to do. This one's saying, hey, square me. So you get 9 plus 6h plus h squared minus 9 over h. 9's cancel, so I have 6h plus h squared over h. What can I cancel from every term? H, so I end up with 6 plus h. This is the limit as h approaches 0. Plug in a 0 for h. Your answer is 6. Okay. Oh, there goes my earring. I'll fix that later. Okay. All right. Last thing we have to do in the last 1 minute. We can do this. 2 types of piecewise functions. You have not equals equals, and you have less than greater than. Not equals equals means that g of x is this function for every value of x on the entire number line except for 1. And it's just this guy at 1. So this guy is a dot. This guy controls the whole graph. Which one do you think we would use for our limit, the top or the bottom? The top. So this limit you just plug a 1 into the top, and that's your limit. So when you have a not equals equals, the not equals controls every single x value on the graph except at that dot. Does a dot affect the limit? No. So you got that. When you have a lefty and a righty, you have a different graph on the left than you have on the right. What do you think you're going to have to do? Different graph on the left than you have on the right. You're going to have to do a left and right-handed limit. Well done. You're Ryan, right? Yes, well done. So for this guy, just for purposes of the video, I know you're all packing up, you have to do a limit from the left, which is this bottom one, because that's where the x's are less than 4. I plug in my 4 on the left, I get 0. If I do a limit as x approaches 4 on the right, I plug into the top, I get 4 minus 4, I get 0. Therefore, what's the limit?
0.
The limit is 0. Ta-da. All right, you're into the lesson. Have a wonderful afternoon. Thank you so much. I know